everyone, McKenzie Ross with OneSpin. I'm here in beautiful Silicon Valley to talk to you about safety and reliability. Let's go for a drive. Automotive systems get more complex all the time. Lane management, braking assist, cars today can practically drive themselves. Vehicle electronics are safety critical. If something in my car malfunctions, I could be injured, or much worse. Fortunately, we have ISO 26262. It's a functional safety standard that covers hardware and software in road vehicles. Trouble is, ISO 26262 is notoriously difficult to satisfy. That's where formal verification comes in. Adding formal to your verification flow can help you meet your coverage goals faster, with fewer headaches and greater confidence. For automotive, aviation, defense, or any safety critical system, if you're not using formal, your design might not have the integrity it needs. As a leader in formal verification, OneSpin partners with chip designers around the world to make electronics reliable. Let's take a closer look at how OneSpin's formal verification solutions can help you to satisfy ISO 26262.
OneSpin's formal verification solutions are ideal for safety-critical hardware in many industrial domains. Today, we'll focus on using formal for automotive devices that must satisfy the ISO 26262 standard. ISO 26262 defines two categories of failures. Systematic failures can originate in either hardware or software. These are typically caused by human mistakes during development, such as bugs or coding errors, but they can also be a result of tool problems or methodology issues. Random failures, by contrast, originate only in hardware. They occur during device operation and are caused by physical effects of the operating environment. In the case of systematic failures, a rigorous verification flow is critical to catch all bugs during development while tracing design requirements. For random failures, safety mechanisms are used to make the hardware fault-tolerant and to detect errors that happen during operation. An example of a random failure in the automotive realm might be one caused by radiation corrupting the memory of an SoC while a vehicle is in motion. Engineers need to make sure that safety mechanisms are carefully verified. They must also perform a quantitative analysis of their effectiveness in catching errors and determining diagnostic coverage. Let's examine what a rigorous ISO 26262 compliant verification flow looks like. ISO 26262 demands an accurate tracing of requirement fulfillment throughout the development process. Each requirement maps to features and sub-features in the hardware implementation plan. Each feature must also have goals associated with it in the verification plan. Finally, test and coverage results are mapped to verification goals to close the loop and to ensure that all hardware requirements have been implemented correctly. Assertions are ideal to express verification goals concisely and directly. They can be used for both simulation and formal. OneSpin 360 DV can perform an exhaustive check for both local and abstract end-to-end assertions. If an assertion is proven, then we know that the hardware feature will work for all corner case conditions. Simulation alone can't deliver this level of confidence. OneSpin Quantify can be applied to this set of assertions to track progress using familiar coverage metrics, including statement and branch coverage. This allows us to ensure that the assertions cover all hardware functions. Simulation and formal process results can be merged to achieve the overall coverage goals. We've looked at addressing systematic failures. Now let's explore how safety mechanisms can be used to prevent or control random failures. For example, radiation corrupting a memory bit in an automotive SoC might cause a failure while the car is on the road. In a modern automotive SoC, we can have many different types of safety mechanisms. These might include self-testing routines running periodically to detect malfunctions, duplicated cores running in lockstep, or error-correcting code mechanisms and watchdogs to protect memories or bus transactions. Engineers have two critical verification tasks. They need to ensure that the safety mechanisms have no bugs. Otherwise, these mechanisms could end up creating dangerous situations instead of preventing them. They also need to ensure that the diagnostic coverage of the mechanism, that is, the proportion of potentially dangerous faults versus detected or corrected faults, meets the ISO 26262 Automotive Safety Integrity Level, or ASIL, target. For applications such as controlling the inflation of an airbag, the hardware may have to reach the ASIL-D target. That means that engineers might need to demonstrate that the hardware has a very high diagnostic coverage, as high as 99%. What are the challenges in performing these two tasks? First of all, we have a huge number of fault scenarios to consider. Think about analyzing the effect of stuck at 0 and stuck at 1 faults on all the nets within an SoC. Even if we look only at the safety critical part of the SoC, we're still dealing with millions of fault scenarios. We may have to analyze the effect of multiple simultaneous faults, which makes matters even more complex. Depending on the specific task and development stage, the analysis might have to be done on both the RTL and netlist. As a result, we need solutions that work at both abstraction levels and can efficiently handle tremendous numbers of faults on complex designs. Let's look at a simple example of a safety mechanism, an error-correcting code, or ECC, protected FIFO. The safety mechanism can be implemented through a Hamming encoder and decoder, leveraging redundant bits in the memory. Radiation can flip bits in the FIFO memory. The safety mechanism can detect and correct single-bit errors. Though it can also detect double-bit errors, it cannot correct them. In this case, it must report the error through an alarm output. Let's consider the first task that we need to perform, the functional verification of this safety mechanism. First, engineers should ensure that the safety mechanism does not interfere with the normal FIFO function. If there are no faults, then no correction is made and no alarm is reported. In the case of a fault scenario where one valid bit in the memory is corrupted, the safety mechanism is expected to detect and correct this error. If input stimuli activate a fault that could be in any of the memory bits, we need to make sure that the effects are detected and corrected by the decoder. We also need to verify that all of the normal FIFO outputs, such as read data, full, and empty, are not affected. We observed that our users were developing dedicated environments for this verification task, typically to control the injection of faults in the RTL model, and then to check specific assertions depending on the faults that were being injected. To facilitate this task, we designed the Fault Injection App, or FIA. This automated app provides a simple interface to inject faults and map assertions to fault scenarios. It reduces development effort by adding dedicated debugging features. These are very important. It can be really confusing to debug a hardware function that is only activated when the design's behavior is corrupted on purpose. The other great thing about this app is that engineers don't need to create a different verification environment. They can seamlessly verify design behavior with and without faults. This also includes the use of OneSpin's quantify coverage technology to track overall verification progress using functional and structural coverage metrics, such as statement and branch coverage. Both the Fault Injection app and Quantify are included in OneSpin 360 DV Verify. Now, let's look at the diagnostic coverage task for the same simple circuit. For ASIL-D applications, engineers might need to prove that no more than 1% of faults will lead to a failure. We know that the hardware is tolerant against faults in the memory, but what about faults in other parts of the circuit? Let's consider a fault in the encoder logic. If we could prove that for any input stimuli activating this fault, its effects are always blocked somewhere in the circuit and never affect the outputs, then we could mark this fault as safe. This is typically hard to do using other mechanisms, but would help in achieving the target diagnostic coverage. On the other hand, if a fault can propagate through the circuit under certain input stimuli, this is noted as a dangerous fault. Looking at how the fault propagates can help improve the safety mechanism in the event that the target diagnostic coverage is not achieved. OneSpin's Fault Propagation App, or FPA, accelerates the diagnostic coverage verification flow. The app has two modes of operation, a fast mode and a deep mode. In general, fault simulators are used extensively for this task. By applying the fast and deep modes at different stages in the fault verification flow, we can dramatically reduce both simulation cycles and engineering effort. Let's look at this flow in detail. The flow starts with a large fault population. If the user does not have one already, this can be computed by the FPA. In essence, this is a list of all the faults that we need to classify in order to determine the diagnostic coverage. Initially, all faults are considered potentially dangerous, or in other words, potentially propagatable. The FPA can be applied in fast mode to this large population of faults. It has dedicated formal verification technology under the hood to perform a fast propagation analysis of all faults in the population. It will detect many safe faults, that is, faults that cannot propagate to critical outputs or internal registers. This analysis may not find all of the safe faults, but the key here is to find most of them in a short time. This expedites the fault simulation process substantially. These safe faults will not need to be simulated, as we already know that they will not cause failures. They immediately contribute to achieving the target diagnostic coverage. The remaining faults are still considered potentially propagatable. Fault simulation can demonstrate that many of these would be detected by the safety mechanism. At this point, target coverage will often not have been achieved, making it necessary to manually analyze the remaining yellow faults. This time-consuming process either results in improvement to the simulation environment to demonstrate that more faults are detected, or it provides arguments to claim that some faults are safe. Both of these strategies aim at improving the diagnostic coverage figure. The FPA in deep mode can perform these tasks automatically and classify the remaining yellow faults as either safe or propagatable. Deep mode is slower in analyzing the small number of remaining faults, but it automates a task that would otherwise require tedious, expert engineering effort and more simulation. In summary, the FPA is a push-button formal verification solution that identifies safe faults in large RTL blocks or netlists. It can also help to improve safety mechanisms by finding tricky input stimuli that demonstrate how a fault could propagate and be dangerous. This app integrates with leading fault simulators, saves substantial engineering effort and simulation time, and increases diagnostic coverage. The Fault Detection app, or FDA for short, is another member of our portfolio of safety-critical solutions. This automated app identifies dangerous faults that are missed by safety mechanisms. It partly replaces the fault simulation effort by providing truly accurate diagnostic coverage metrics. Let's recap. We have looked at the verification of hardware safety mechanisms and examined how formal verification can be a huge asset in developing safety-critical hardware. Assertions and formal verification are a great fit to achieve high confidence that hardware requirements are correctly implemented. They also allow us to simplify the tracing process. The Fault Injection app provides a consistent way to control the injection of faults and verify safety mechanisms under all relevant fault scenarios. The other important task we looked at was the determination of the diagnostic coverage of safety mechanisms. Here, we saw how the Fault Propagation app provides a push-button method to identify safe faults, improve diagnostic coverage, and ultimately reduce the simulation and engineering effort necessary to achieve target coverage. We also looked at the Fault Detection app, which is a silver bullet when it comes to identifying dangerous faults that are missed by safety mechanisms. OneSpin has years of experience in the application of formal verification techniques. We operate on the cutting edge of safety-critical hardware. Customers such as Bosch and Infineon apply OneSpin's tools and methodology for the development of complex automotive SoCs. We've only scratched the surface of safety-critical in this video. To learn more, take advantage of the resources available on our website. If you design or verify safety-critical hardware, or if you use fault simulators to determine the diagnostic coverage of hardware or even software safety mechanisms, OneSpin can help. Visit onespin.com/safetycritical to download our ISO 26262 white paper, which examines the standard and the coverage benefits that formal verification tools can offer. More information on OneSpin's Fault Injection app, Fault Propagation app, and Fault Detection app can be found at onespin.com/solutions/safety-critical-verification. Finally, if you want to keep up to date with the latest functional safety headlines, subscribe to our newsletter at safetycritical.onespin.com. It's a fantastic way to stay informed.
Thanks so much for joining us today. I'm McKenzie Ross with OneSpin. We'll see you next time.